faculty in Planetary Engineering. And I'm going to be speaking today about a part of mathematical foundations for BME that has to do with how do we extract the most informative or most relevant features from high-dimensional data sets. Before I get started, I wanted to get a little bit of background from everybody. So I want to ask a few questions. Very simple. How many of you knows eigenvectors and eigenvalues? Everybody? What about singular vectors and singular values? One. Okay. What about the method of Lagrange multipliers? Okay, half of you, more than half. Okay, so that's good. Okay, that's good. What about, no, I think this you should know. So. All right, so what is this lecture and the next going to be about? It's going to be about this question of dimension reduction and what is dimension reduction about. The reality is that in many disciplines, and today I think I mentioned computer vision, medical imaging, robotics, bioinformatics, we're just inundated with many kinds of data. Let me give you some concrete examples. How many of you have used Snapchat? All right. So do you guys know how that works under the hood? Do you know how many pictures have, or since the arrival of Snapchat, how many extra pictures there are in the internet every day? Okay, so if you just plot the number of pictures, it just grows at a rate of about 50% every year, roughly. So in a couple of years, it just doubles. And you can see that once Facebook appeared, and then when Snapchat appeared, you can see the big bars increasing. So the amount of data is just exploding. These data sets are incredibly big. The number of megapixels in an image is just growing. If you think about MRI scans, now you have 3 dimensions. So that's what medical imaging is about. What you see at the bottom left is, anyone who can guess what you see at the bottom left? DTI, someone said. Anything else? All right. So there is a technique called diffusion MRI, where you get an MRI scan, but you get one MRI scan for every possible direction in the brain that you want to acquire. The number of directions could be 30, 40, 50, 200. And so now it's like from every patient, you get 200 MRI volumes. And each MRI volume might be 1,000 by 1,000 by 100, and then you get 200 of those. And now you need to take those and be able to extract the connectivity of the brain, figure out which regions are connected, and that's just a drawing of the fibers extracted from diffusion MRI. So again, these data sets are massive, quite big. So what do you do about it? What you see at the bottom right, that is the so-called Da Vinci robot. I'm sure you go to homework, you can see it. It's in Hackerman Hall. Once you pass through the hall, there is one of them. So over there, the type of data that you collect is maybe smaller. It's position and velocity of every joint as a surgeon is doing a particular type of surgery. But there is also a stereo pair from which you can collect data about the performance of a surgeon doing some surgery. So there is a project led by Greg Hager whose goal is to be able to assess what is the level of skill of a surgeon at doing a particular surgical procedure. So say you take a particular surgical procedure, then you take a task that might be suturing, then you want to figure out at any time instant whether you're grabbing the needle, inserting the needle, passing the needle through the tissue, or so on and so forth. And then you want to figure out how well you're doing it. And this is particularly useful when you're training surgeons to do surgery. So how do you take those volumes of data and extract relevant features from which you can solve these tasks? So as it turns out, the data is big. I talked about megapixels in an image. But the reality is that the dimension, the intrinsic dimension of the data set is sometimes small. So I like to give some concrete examples with something you can relate to. So these are just pictures. These are the pictures that you have in Facebook. And maybe this picture is not super well representative, but what I'm trying to illustrate here is, suppose that you've got pictures of a single individual, and suppose that all you do is to change the lighting conditions. Okay. So as it turns out, the dimension of every picture might be 10 to the 9 pixels. Okay. But as you change the lighting direction, the light has essentially 3 dimensions, right? It's just the direction in which the light hits the surface and then goes back and projects into the image. Okay. So if you have super simple objects, think of a sphere, and suppose that the sphere is painted of something super simple that is not very reflective, like a matte surface. That's the simplest model that can be used about light in computer vision. So what happens is that even though this picture is 10 to the 9 pixels, intrinsically there are only 3 dimensions that vary as I change the lighting conditions. In fact, let me get into the extreme. So look at my face and imagine that you're taking a picture, and this is what I'm doing. How many degrees of freedom are there? Anyone can guess? A million? What happened between one picture and the next? Just one. I just rotated my head. So in fact, even though the picture lives in millions and millions of dimensions, it describes just a curve. So the intrinsic dimension is just 1. Okay? So changing rotation in one direction is just 1 degree of freedom. If I move my head like this and like that, then it's 2 degrees of freedom. So likewise, if the head is fixed and all I'm doing is just changing the light, it's typically 3 dimensions. So the intrinsic idea is that if I take all millions of pictures of a single individual and they're all lighting conditions, it can be actually very well approximated by something that intrinsically has 3 dimensions. What is even more striking is that it can be well approximated by something that is linear. Okay? And so in fact that's true when you change illumination. When I'm rotating my head, is non-linear, as you can imagine, right? Because there is a rotation being involved. And in this particular case, it's not great. You see other kinds of variations. And you see the person is sort of smiling and then it's a little bit sad. So those phase variations also add extra dimensions. And so you can immediately see that if you want to recognize if someone has autism by looking at facial expressions, then that's going to add extra dimensions. And this is no longer going to be linear. So the only case that is linear is changes in light. Okay? But rotations and expressions are non-linear. Okay. Second example that I'm going to show here, also with pictures. Suppose that I've got this picture, and as you can see, there is a zebra, there is a background, there is water, and so on and so forth. Pretty much everybody has compressed your images once in your life. Have you compressed your images? Have you had issues sending an email that the image was too big? You compress. Okay, what is the basics of the algorithm of compression? You actually look at patches. You take tiny, teeny patches, and you figure out that in fact when you look at patches, maybe many things are repeated. So you don't need to encode every single pixel. You can actually look at representations that are simpler because there is some repetitiveness of the patches. So as it turns out, what you can possibly imagine is that if I look at all of the patches that contain a zebra, okay, possibility number 1, they're all identical. It's not true, but bear with me for a second. Suppose that they were all identical. What happens if I put all of these patches and I vectorize them, and I put them one next to each other into a matrix, and they're all equal to each other? What is the rank of that matrix? Linear algebra 101. If all of the columns of the matrix are equal to each other, what is the rank? 1. Okay? Now there's going to be a little variability because these zebra patches are not all identical to each other. But I think it's a reasonable, good, practical assumption to say that they're going to be, if I have 1 million patches, maybe there are 3 linearly independent, maybe there are 10 linearly independent. So the fact of the matter is that these patches, even though they're big, maybe it's not millions and millions, but it can be a 1,000-dimensional patch. If it is, if it is 10 by 10, it's 100 dimensions. But if you take a patch that is 50 by 50, already it's 1,000 dimensions, more or less. But maybe the rank is 2, maybe the rank is 3. So the idea is that all of the zebra patches maybe form one subspace, and all of the water patches maybe form another subspace. And now I reduce the dimensions from millions, which is the original image, to 3 dimensions for the zebra, 3 dimensions for the water, and so on and so forth. And that's a way to compress in a way that is adapted to the data. Let me give you another example. This is actually a video taken in Homewood campus in, I think it's Charles Street. And so what you see some dots here. So you see some yellow dots in the background, some blue in the car, and some red in the other car. Okay. Those dots correspond to just, you pick a point in the car and you track it. So this gives the trajectory. So as it turns out, and here you have to believe me, is in fact pretty much everything I've said you have to believe me, I haven't proven anything. But if you think of all the blue trajectories, and each trajectory is now a long vector. Y, well, every pixel is 2 coordinates, x and y. And now I have 100 frames in a video, so a vector of dimension 200. So all of those trajectories that correspond to the blue car, they might be several hundred dimensions. If the video is very long, they might be very long. But they also live in a subspace of dimension 3. And why is that dimension 3? Again, because the movement of the car in 3D space is just rotations and translation. And in fact, if you have a car that goes in a straight line, at constant speed, is probably dimension 1. It's just because the car can also rotate and translate that you get a few extra dimensions. So the generic case is that it's just 3 dimensions. So again, you can take complex data and complex video in time now, and they describe a low-dimensional subspace. Big dimensions, but the intrinsic is small. Let me finish with politics. So this was a long time ago. It was not the last election, but it was the previous one. So this is one of the debates between Hillary and Obama. And again, let me go back to the same example. Suppose that I had a video, but it's now a still. So it's a frozen picture of Obama. Every frame is identically the same. What is the rank of that matrix if I put one picture of Obama in every column of the matrix? The rank is 1, as we said earlier. Right? If I have a matrix that all of the columns are identical, it's rank 1. So the idea here is that the video can be decomposed into a sequence of events. So this is the Obama piece of it, frontal view, and there was a little variation. Now it's the public and it's zooming out just a little bit. So when you do that, the frames are not identical, but they're somewhat very related to each other. So you can assume that there are linear combinations of each other. So even though I might have 10,000 frames of Hillary in that piece of the video, maybe only 3 are linearly independent. Okay? So that's exactly what dimensionality reduction is about. It's about taking big data in big dimensions and extracting 1, 2, 3 dimensions that are the most meaningful. In some cases, we get very, very lucky, and the data can be well approximated by a linear subspace. And I gave you many examples where that's the case. And to go back to faces, which is the one that I've highlighted the most, faces under varying lighting conditions, that's a single linear subspace per person. In some cases, it's low dimensional, but its surface is curved, or more generally, it's a manifold. That's the case of when I said I'm rotating my face. That's an example. I get a nonlinear manifold. It's not linear. Can someone very intuitively prove to me that 2 pictures on the different orientations don't give a linear manifold? Does anyone remember from linear algebra what is a linear space? If I've got 2 vectors, and I take the average of the 2, it needs to belong to the space, right? That's basic. That's what linear is about, right? Okay, what would happen if I take a picture of me looking that way, a picture of me looking that way, and now I average the pictures? Any guesses? In fact, if I've got a picture, for the sake of simplicity, that has something like here, and the other picture has something like here. And now I add them up and divide it by 2. What do I get?
A blurry version of the same.
I'm going to get a blurry version. I mean, well, first of all, if they're completely disjoint, I'm just going to get something like this, right? But if they happen to overlap a little bit, I might get something like this, right? So do I get a face of a single person?
No.
So do averages of faces look like faces? No. That's why the illumination is true, because they're all tight pictures without changing the pose, and all you do is to change the light. Okay, then when you average, you don't see a ghost and 2 faces, one top, right? You just change the amount of light. That's why these changes of illumination is linear, while the changes of pose is not linear. And that's the distinction between that and that. Okay? And here you've got a union of subspaces. That happens because I've got pictures of 2 different people, and each subspace is for 1 person. Or in the case of videos that I showed before, I had many cars moving. Each car is its own subspace. Okay. All right. So with that in mind, let me now begin the lecture on how do we actually do this, and how do we go from the big data to a few dimensions. So PCA is, without doubt, the single most used method for reducing the dimension of data to a few dimensions that are most important. And the basic principle behind PCA is really as follows. The idea is that maybe I have a cloud of points distributed all over the place, and let's say that that's my data. Let's say it was in 2 dimensions, but obviously I'm thinking millions of dimensions. So suppose that I have x is a random variable. I'm going to assume that capital D is the ambient and big dimension. Okay. And so, so this is going to be the data, if you wish, data point. But I'm assuming it's a generic data point. So it's a random variable drawn from some distribution, and I'm just drawing lots of samples here. So super simple. So Y is going to be what I call the principal component. And the exact definition in words, if you wish, is going to be a linear component of x with maximum variance. Okay, so that's in words. So what it really means is, in this particular picture, I've got any possible direction that I can possibly take. Right? There are only 2 dimensions, and so if I want to reduce dimensionality, the only possible reduction I can make is from dimension 2 to dimension 1. So it's really like finding a single direction here in the data that has the most variance. So if you have to just think intuitively, just look at the picture, right? I'm sweeping all possible directions. Which one is the direction that has the most variance? Maybe it's going to be something like this, perhaps. Right? You believe me? More or less. That's what the intuition says. So let's formalize it in actual equations, how we're going to do that. So first there is this word linear component. Okay? So what that means is that I need to pick some direction, and I'm going to call this direction U. Let me assume that the origin happens to be there. And so what really I mean is that by linear component, what I mean is that I'm going to take the dot product between U and X, or if you wish, U transpose X. Okay. So U is going to be the main direction. And what does that do? It takes every point and projects it here. It takes this point, projects it there. It takes this point and projects. So it just projects the given data point onto the direction that I'm choosing. Okay. If you don't remember, I'm sure everybody remembered, this is just sum of ui xi. That's what I mean in there. Good. So that's the definition of a linear component. Now, among all linear components, and this means among all possible choices of u, I want to pick the one that gives the largest variance. That's the definition. So what I need to do is maximize the variance of y with respect to the choice of the direction u. So find the component that has the largest variance. So that's what I did. Is it clear so far? So far so good? Good. So very good. So, well, okay, so the variance of y is equal to the variance of u transpose x. Right? And if you go to Statistics 101, what is the relationship between variance and expectations? Maybe I should have written it here at the top. So the variance of y is equal to the expected value of the expected value of y squared minus expected value of y squared. Good. Okay. So what I'm going to, so let me begin then with the expected value of y. The expected value of y is just the expected value of u transpose x, right? Now, u is a direction. U is a constant. U is not random. X is random, is any random, it represents the data, but it's any random choice. But u is fixed, okay? So, what can I do with this u? I can take it outside, right? Expectation is linear. This thing is linear. So, this is the same thing as u transpose expected value of x. Agreed? Okay. So I'm going to make this assumption from now on that the expected value of x is 0. Okay, that's why I'm kind of putting the origin here in the middle. I'm going to assume kind of the data is centered, so the expected value is 0. That does not need to be the case, and in fact in the homework I'm asking you to do the case where it's non-zero. Okay. So I'm going to assume that. So this thing is 0 to begin with. So this term in here is 0. I can get rid of it. Mark. So now I'm going to compute the expected value of y squared. Okay, the expected value of y squared. So that's going to be the expected value of u transpose x squared. Right? Good. So now I'm going to do a little tiny teeny trick here, which is that I'm going to write this as u transpose x. Fine. But now I'm going to write x transpose u. I can do that because this is u transpose x times itself. And u transpose x or x transpose u is the same thing. Right? Dot product is commutative. So I'm just writing it as such. It's a scalar times another scalar, and they happen to be the same. Okay, good. But as it turns out now, using the same trick as before, that u I can take outside. So I'm going to get u transpose. And likewise, that u I can take outside. So I'm going to get expected value of x transpose in the middle, and u over here. Okay. So let's compute dimensions now to be very clear, because this was a scalar, this was a scalar, but there are some vectors here. So just to be clear, this u is 1 by d. This x is d by 1. This is the transpose, so 1 by d. And this is still d by 1. So the product of everything is still a scalar. It's just the variance of one variable. But the point being that in between here, I get some matrix, d by d. So effectively, and anyone can tell me what that matrix is? What is the expected value of x transpose?
The variance.
Hmm?
The variance.
The variance?
Covariance.
Covariance matrix. All right. So this is just U transpose. I'm going to denote that with a big sigma, which is the covariance matrix. And I'm going to put a sub x to remember you that is the covariance matrix of x times U. Good. So that's what it is. Okay? So the bottom line is, okay, I did a lot of little tiny teeny steps here and there, but the bottom line is that the quantity that I want to maximize the variance, and I've shown that the variance is equal to U transpose sigma U. So going back to my original problem right there, what I'm trying to do is maximize with respect to U, this quantity, U transpose sigma x, and then U. That's what I'm trying to do. Okay? Everybody with me? It's just maximization of a quadratic. Okay, who can tell me what the maximum of this is? For simplicity, let's suppose that it was just a one-dimensional thing. So this sigma is a constant, right? I'm going to assume that sigma is the covariance of the data. So in fact, going back to my beginning, right, I should have probably stated a few more things. I should have said the expected value of x is 0, and I should have said that the variance of x is sigma. That's what I should have said maybe from the beginning, right? So I give you sigma. So suppose that this is, if this was scalar, this would be sigma u squared. What is the maximum with respect to u of sigma u squared? Calculus 3. What is the maximum of u squared? When u can be anything. Can I let u go to infinity? Yeah, I didn't say anything about that. If u goes to infinity, what happens to u squared? Goes to infinity. So the maximum of this is going to be infinity if I, right? Okay, so something is fundamentally wrong about everything I've been saying so far. So what's wrong? I need some constraint. What is the constraint? Well, if I go back to my little picture at the beginning, right, this u was kind of a direction. And the picture that I got in my head was that I was going to project all of the points on this line, and then I was going to find the variance. And as I changed the direction, the variance was going to be large, the variance was going to be small. So obviously this was the direction with the largest variance, right? But if u is a direction, what constraint do I need to put on u?
The size of it.
The size of it must be equal to maybe 1. I need to fix it. Because if I allow u to be infinitely big, right, this is not going to work. Okay, so I need to maximize this, but subject to the fact that u is unit norm. Right? I need to fix is a direction. It cannot go unbounded. It cannot go to infinity. Okay, so that's where I put my constraint. Okay? And as you can imagine, this thing is the same thing. That's what the norm of a vector is equal to the dot product with distance. Good. Okay, so now we are ready. We've gone from from the problem that I want to do to the actual formulation, and now it looks relatively simple. It's a maximize some quadratic subject to some quadratic constraint. So, how do we do optimization when we have constraints? Lagrange multipliers. And so how do we do Lagrange multipliers? In words is the objective function plus lambda times the constraint. The objective function plus lambda times the constraint. So the objective function is u transpose sigma x u plus lambda times the constraint. Except that you have to remember that you need to have in your head that the constraint is to be equal to 0. Right? So here I have, so the way I'm going to do it is that, well, this is the same as that. I write it as equal to 0 before I get started. And so lambda times the constraint is really that. Okay. So good. Now I do Lagrange. Objective plus lambda times the constraint. What is the next step of Lagrange? Take the derivative with respect to what? Tu and set it to 0. So the partial derivative of L with respect to u. Oh, what is the derivative of u transpose sigma u? Huh? Sigma x times u? Huh? Times 2. Great. Very good. Anyone who does not know why the derivative is 2 times sigma u, raise your hand. Otherwise, I'm going to go 10 times faster. It's clear to everybody? Okay, good. Now, what is the derivative of this? Minus 2 lambda u. Okay, good. And you guys said that I needed to set these to 0. So take the derivative and set it to 0. Good. So if I do that, right, from here I get that this is equal to that, right? So this is a d by d matrix times a d by 1 vector. This is a scalar and this is a d by 1 vector. So a matrix times a vector is equal to lambda times the same vector. Have you ever heard of such a thing in your life? What is it? Eigenvector, eigenvalue. So I conclude that u lambda comma u is eigenvalue, eigenvector of the covariance matrix sigma. So lambda is an eigenvalue and u is an eigenvector. But is, given a matrix, there is just one eigenvector and one eigenvalue? Or there's more than one? Huh?
D.
Generically, if the matrix is d by d, how many eigenvalues there are?
D.
D. And generically, there are d eigenvectors. It's not always the case, but that's the generic. So all I've proven insofar is that the direction that I'm looking for, the direction that maximizes the variance, is an eigenvector. But I don't know yet which one of them. Right? There are many of them. Okay. So I need to continue. To continue, I need to figure out which one of them. Okay, so starting from that equation, I have now the following. So sigma x times u is equal to lambda times u. That's what I have. So let me multiply on the left by U transpose. So I'm going to get U transpose sigma x U is equal to lambda times U transpose U. Correct? I just multiplied on the left by U transpose. So far, so good. But look, it so happens that U transpose U is equal to 1.
No.
So this is just equal to lambda. So the value of lambda is equal to the value of this thing. But that thing is the thing that's here. So what I've proven then is that I'm trying to maximize this. That's what I want to maximize. So if I've got many, you guys said, okay, let's say it was a 3 by 3 matrix for the sake of simplicity. So I've got 3 eigenvalues potentially. And I'm trying to maximize this quantity. And this quantity is equal to the lambda that I'm looking for. So which one of the eigenvalues should I pick?
Biggest.
The biggest. So what really, back to lambda star, U star, is equal to the largest eigenvalue and eigenvector. Okay. Good. But now I'm remembering like 50 years ago I took linear algebra. And I think I remember that the eigenvalues were the roots of some polynomial. And I remember from that past life that it can happen that these eigenvalues are complex. But they don't have to be real always, right? So suppose that I had a 2 by 2 matrix and that the 2 eigenvalues are complex. Which one is the largest? Can you tell me? What do I do then? Is this right? Take the absolute value. Well, but it would be kind of weird that after all, I was computing the variance, right? The variance better be a real value quantity, better be non-negative. So if the variance happens to be equal to lambda, and that lambda happens to be complex, something's probably gone wrong. Okay? So now, this you may have learned in linear algebra, you may have not. But here is something that is important. The sigma is equal to sigma transpose. In other words, the covariance is symmetric. The covariance is symmetric. So it's not any matrix, it's symmetric. Okay? And once you have something that is symmetric, the eigenvalues of sigma are always real value. Okay? This is true for any symmetric matrix. So symmetric matrices always have real value, real eigenvalues. Okay? Keep this here because this box I'm going to complete in a moment with extra information. By the way, this is the first question of the homework, to actually show that the eigenvalues of a symmetric matrix are always real. Okay, because they are real, we can always pick the largest one. Okay? Is that clear? But there is something else that could go wrong. They can be real, but what if they're all negative? I'm going to get a negative variance? Probably doesn't make sense. Okay. So another property is that the eigenvalues of sigma are non-negative. Okay? That's another property that covariance matrices have. Okay, so far so good. So, what is the recipe? Given data, given a big data, how do I find the first and most important principal component? Well, you compute the covariance matrix. That's the first thing. You compute the eigenvector of the covariance matrix that has the largest eigenvalue. And that gives you the U. And that gives you the main direction. And then you compute Y by projecting. So you just take every data point and you do dot product with that direction. And that's going to give you all of these data points. And that's going to give you the first principal component. Is that clear? All right. Well, do you think that you can do things in just one dimension? Well, in medicine we like that, right? You just measure the temperature or the pressure. But in fact, we want more dimensions, typically. And in fact, many data sets for many of the things that I gave in the introduction, you need 3 dimensions or 4 dimensions or what have you. So this is just the first one. So let me move to the next step then, which is, that's why it's called principal components, because there are many of them. So principal components. So it's now going to be many of them, y sub 1, y sub 2, y sub d is equal to the d uncorrelated linear components of x with maximum variance. Okay. So typically, and just to put some order, we're going to say the variance of y1 is bigger than or equal to the variance of y2, bigger than or equal to the variance of y3. Y sub p, sorry. Okay, so let's just try to find the second principal component. So what changed from the first definition to the second definition? Linear component of x with maximum variance. What is the big new word that appeared there? What is the big new word? Uncorrelated. So that's the main thing. Okay. So what I'm going to have now is y sub I is going to be equal to u sub I transpose x. So that's the same thing as before. These are linear components. Okay, and so I goes from 1 to d. And now they need to be uncorrelated. Okay. So what does it mean to be uncorrelated? Anyone remembers? Say it again.
So U1 and U2 would be.
Well, let me just go to basic probability and statistics. I have 2 random variables and they're uncorrelated. Why does it have to do with being perpendicular or not? I just have 2 scalar random variables. The covariance is 0? I think I like that. So remember that, by the way, the expected value of these guys is still 0, right? That's because the expected value of x is 0. It's the same derivation as before. So uncorrelated really means that the expected value of the product of 2 of them is 0. Pretty much what's your name?
Melody.
Melody. Pretty much what Melody said. Okay. That's what it means to be uncorrelated. Okay, so what does this mean in practice? Well, let me write it down. The expected value of what is y sub I? I've written it there. That's u sub I. Okay. Y sub j now. I'm going to do the same little tiny trick that I did before of putting the second piece backwards. Okay. So this is going to be x transpose uj. Everybody with me? Do you agree? Do you agree? Good. All right, so what am I going to do now? I'm going to take these out. And uj. I'm just take the constant outside of the expectation. And what do I get in the middle? What do I get in the middle? Exactly that. So this is equal to u1 transpose sigma x uj. Very good. And that has to be equal to 0. Okay, maybe I should even put that thing here. Expected value yi, yj is equal to 0. Okay, good. Yeah, I kind of had a very simple condition and I made it more complicated, but I have no clue still why this is helpful in any way. Okay, I got that. Okay. So let's see what we can do. Let's see what we can do. Okay, so let's just do it for the two principal components. So let's say that U1 is the first and U2 is the second. Or sorry, Y1 and Y2. First and second principal components. Well, for the first one, I hope I already know what the answer is, right? Ah, I have it here. That's the first principal component is going to be, it needs to be an eigenvector and eigenvalue, and in fact it's going to be the largest. We already proved that. So this equation that I just wrote becomes U1 transpose sigma U2 is equal to 0. That's exactly what I wrote there, I just wrote it here. But U1 is an eigenvector, right? So the eigenvector times the matrix, what do I get? Well, probably I have it here, no? I have it here. The matrix times the eigenvector is equal to lambda times the eigenvector. It's just that it's transposed, right? So just look at it that way, right? So, U1 transpose sigma is what? Lambda 1, U1 transpose. Agreed? Sigma, no, the sigma I just got rid of. Don't, no. U2. All right. Agreed? Because that guy is an eigenvector, I can do that. Okay. Now, lambda 1 was supposed to be that variance, right? The largest variance of all the variances possible. Unless the data is super degenerate, that everything is at the origin, right? That variance better not be 0. Right, so I'm going to assume that lambda 1 is strictly positive. If that's the case, and the product of these things is 0, what needs to be 0? That part, right? So, U1 transpose U2 is equal to 0. So, if two vectors, the dot product is 0, it means that the vectors are perpendicular to each other. Right? So, U1 is perpendicular to U2. Okay. What's your name?
John.
John. So John said at the beginning, I said, what is uncorrelated? And he said, they're orthogonal. And I didn't say, but I said, are you kidding me? I have random variables, they're scalar, there's no orthogonality. And I went my own way to say, no, statistics, uncorrelated, it means the expectation, that's what it means. But see, he was right. But he just didn't say it entirely right. So, the y variables are uncorrelated. That implies that the directions, U1 and U2, are orthogonal. Okay? So that's how we go from statistics to the geometry of the problem. Okay? The random variables are uncorrelated, but it means that the directions of projection are orthogonal. So going back to my picture on the far left, if this is U1, What's the only option I have for U2? Because this is 2 dimensions only. What's the only option I have for U2? Like this. Right. That has to be U2. And this needs to be perpendicular here. Okay? And obviously I draw my data in a very, very convenient way so that it really looks like almost like an ellipsoid, right? And what's really going on is that this is the major axis of that ellipsoid, and that is the second major axis of the ellipsoid. And in fact, even this distance here, that's going to be lambda 1, and this other distance here is going to be lambda 2. So that's why the directions end up being perpendicular to each other. Okay? So, in conclusion, before I get into in conclusion, wow, I've got 2 eigenvectors, and they need, well, I didn't even prove anything yet. I just derived the constraint, in fact. I didn't prove that U2 was eigenvector of anything. All I did was uncorrelated, that means orthogonal. But I still need to redo the whole problem. I need to go and say, okay, let's find now the second principal component. And I went a little bit ahead of myself by saying it's an eigenvector. I don't know yet. So let me continue. So far, to summarize, principal components are linear projections of the data with largest variance. How are they obtained? The first one is the eigenvector corresponding to the largest eigenvalue. The second one needs to be uncorrelated, and so the direction is orthogonal. But I don't know what it is yet. I don't know what it is. So let me figure out what is U2. So for U2, well, I need to maximize the variance again, right? Components of largest variance. So it's going to be the same thing, maximize, right? I'm just going to put some little extra notation. So I'm going to call it U2 because we want to find U2. Maximize U2. Such that, well, U2 needs to be unit norm, so that's the same. So in fact, let me even just write it. 1 minus U2 transpose U2 is equal to 0. But what else do I need in addition? Maximize the variance. The direction needs to be unit norm. But if I just do that, I'm going to get the largest eigenvector again. So what else do I need to say?
It's orthogonal.
It's orthogonal to the previous one that I already found. So I need to say that U1 transpose U2 is equal to 0. Okay? So I'm going to put a 2 there, and a 2 there, and a 2 there, and a 2 there, because I'm just very lazy. But I need to add, and I'm going to put a lambda 2 so that we don't confuse each other. Okay, good. But now I need to add these extra constraints. So what do? Objective plus lambda times the constraint. What if I have 2 constraints? 1 Lagrange multiplier per constraint. So I need to just add, maybe I'm going to put gamma U1 transpose U2. Right? Fortunately, that already had the 0, so I didn't have to do anything with that. Agreed? That's the Lagrange multiplier story. Objective, lambda 1, constraint 1, lambda 2, constraint 2. So now it's the same procedure as before, and you guys already know how to compute the derivatives, so I'm just going to go and write them down. So these guys, I think you said 2 times that. For this one, I think you said 2 times lambda 2 U2. That's the same we did before. No change. Derivative of this with respect to U2, what do I get? Plus gamma times U1 transpose. I hope that one of you is very upset at me right now.
No transpose.
No transpose, no transpose. Why no transpose? Well, just, this is d by 1, guys. This is d by 1. If I put a transpose, this would have been 1 by d, right? So never sum apples and oranges. So this needs to be like that. Okay, good. Okay, good. So now, what am I going to do? Well, this needs to be equal to 0, I guess. So let me multiply by U1 transpose on the left. So I'm going to get 2 U1 transpose sigma x U2 minus 2 lambda 2 U1 transpose U2 plus gamma U1 transpose U1 is equal to 0. I just multiply by U1 transpose on the left. Okay? Now, what happens? U1 is fixed, is the eigenvector that I already have from the previous. So what is U1 times sigma x? Apparently I just did that somewhere, no? I got that? Yes? So what do I get? 2 times lambda 1 U1 transpose U2. Agreed? Minus 2 times lambda 2 U1 transpose U2 plus gamma. What is U1 transpose U1? 1. That was a unit vector from the previous part. So that is just that. And if you just put these two things together, you get 2 times lambda 1 minus lambda 2 U1 transpose U2 plus gamma is equal to 0.
Isn't U1 transpose U2 0?
But exactly. U1 transpose U2 is equal to 0. So this whole thing is actually 0. So this means that gamma is 0. So yeah, I added an extra constraint of orthogonality and all. But Lagrange tells me, oh, the Lagrange multiplier is 0. So it's as if it was not there. If it is as if it was not there, then it has to be an eigenvector again, because, and let's see it. I go back where if gamma is 0, well, here, right? If I substitute in here that gamma is 0, what do I get? Now this must be before I take it. So from here, right? Gamma is now 0. And the 2's cancel. So don't I get sigma x U2 is equal to lambda 2 U2? Everybody got that or not? Okay, so it's exactly what I said. I had an extra constraint, the Lagrange multiplier is 0. So I'm back to business. It still is an eigenvector, an eigenvalue. It's the same thing we did before. I'm not going to continue now. But it cannot be the same damn thing as before, right? It needs to be an eigenvector, an eigenvalue, U2, that happens to be orthogonal to U1, because it must satisfy that extra constraint in any case. Okay? So now, I tell you, you've given a covariance matrix, and you found the first eigenvector, and now I'm telling you find the second one. But typically, the second one is whatever it is. Does it have to be orthogonal to the first? Or not? Usually not. If I give you a random matrix, and you compute the first eigenvector, and you compute the second, they can have any angle with each other. Okay? So that's why I left my box here. But the matrix is symmetric. And symmetric matrices are very nice matrices. They have real eigenvalues. The eigenvalues are non-negative. And the eigenvectors can be chosen to be orthogonal. In general, but in fact, if lambda 1 is different from lambda 2, then U1 has to be orthogonal to U2. If the eigenvalues are distinct, the eigenvectors have to be perpendicular. That's a particular property of symmetric matrices. So in this particular case, because I'm not computing eigenvectors of a random matrix, it is a covariance, it is symmetric, it's nice, everything, the stars align together. The eigenvalues are real and they are non-negative and they are perpendicular to each other. So indeed, because of that box, I conclude here that lambda 2 comma u2 is second eigenvalue eigenvector of sigma. That's the conclusion. And from now on, I'm just going to hand wave. If you have to compute 3 principal components, it's going to be the top 1, top 2, and top 3. If you have to compute the top 10, it's the top 10 eigenvectors and eigenvalues. You believe me, the rest is, the proof is in the book, the handouts that I give you. Okay, but I hope it's very clear now why, and I think this picture is very illustrative. That's the largest variance, the second largest variance. You can imagine that if this was in 3 dimensions, you would have an ellipsoid, and it will be the third direction. Is that clear? Okay. So that's it. Those are the, that's what PCA is about. So you will see in many talks, particularly in medicine, that they say, we took the data and we found the principal components, and for that application, they start to do interpretation that this is that, this is that, this is that. I hope you learn from this lecture that they have no interpretation whatsoever. They're just directions with largest variance. The first largest variance. And the fact that they happen to be interpretable might be particular for one data set, but that can completely change from data set to another. Okay. One more thing, because you will have it in the homework that, for today, is what if the data is not centered? Okay. You will derive everything else, but you will see that everything is the same. Everything is the same. The only thing is that before I get started, you know, if the origin was here, I just need to move things to the center before I get started. So there is always a computation of the mean. Right here, I assume that the mean is 0. In reality, when you apply these to data, there is always going to be 2 things you need to do. One is you need to compute the mean of the data. The other one is that you need to compute the covariance matrix, and then you compute eigenvectors and eigenvalues. Okay? So let me illustrate this now with some examples. So I'm sure you see today that you can pick up iPhoto and you have all of the pictures of you, and you click on which pictures are of you, and iPhoto is so nice at producing other examples of pictures of you, and it gives you nice bounding boxes. So all this question of detecting faces, recognizing faces, today is sort of pretty much given technology that you can put in your iPhones. Okay. But this was not true, or has not been true before. So in the 80s, in the 70s, in the 2000s, technology for recognizing faces was just under development. And so the very first success, the simplest and first successful algorithm for recognizing faces is called Eigenfaces. And it's called Eigenfaces because all it was done is to apply PCA to the database of images of faces. So projecting the data from million dimensions to a few. And then it so happened that in that subspace, the images of individual 1 were around here, the images of individual 2 were around here, and then it was easy to classify. Okay. And so eigenfaces, and I'm going to show you pictures of what eigenfaces look like, are exactly the U1 and U2 are going to be the eigenfaces. But before I begin, this is the data. So these are all pictures of one person, and what you can see is that the lighting conditions checked. So this is probably a frontal view with the light probably frontal to the individual. I guess here, potentially the light is all from the left, maybe a little bit upright because you can see the top right of the nose being illuminated, but the rest is very dark. and so on and so forth. So you can just imagine all possible directions being put into. In particular, I think in this case is 10, well, this is 10 different illumination conditions. But I think this database has probably 64 different lighting conditions. So that's the data. So what we are going to do is to take these images, which are 2 dimensions, okay? And we are going to vectorize them into a single vector. So a single image just becomes one of my data points. And these images are 192 by 168, so I don't know how much that is, but a few thousand dimensions, whatever that is. Okay. So let's say it's 1,000 to make my life simple. So I have a 1,000-dimensional vector that corresponds to that picture. Okay. And every entry of that vector is a different pixel, and is the light for that pixel. Now I'm going to have one individual and 60-something illumination conditions, whatever. So the matrix is 1,000 by 60. That's my data. Okay? So it's like having 60 points in a space of dimension 1,000. So what are we going to do? We are going to compute the average of all the faces. That is exactly the first step that I never emphasize and talk about. But it's really, you're going to prove that's in the homework, that when the data is not center and is not zero mean, you have to compute the average. So that's the average of all the faces, and it does not look like ghost or anything weird because all faces are perfectly aligned, they're equally cropped, is the same, so all what's changing is the light. And so if this point has no light in one image, it will have a lot of light in the next, and the average is going to be more or less looking normal. That's why it really looks like the light is just illuminating your front, because it's sort of the average light condition. But now you see what the eigenfaces look like. So this is U1, and this is U2. But how is this going to be U1 and U2? They were vectors, right? So again, let's think about it again. My matrix has dimension 1,000, I said, by 60. Okay? What is the dimension of the covariance? So the x vector, every x vector has dimension 1,000. All right? So the covariance matrix is going to be 1,000 by 1,000. Agree? So the eigenvectors of that matrix, what dimension are they going to have? 1,000. So the first eigenvector, the U1, has 1,000 dimensions, a long vector. But then I reshape it into a matrix again so that it looks like an image. And then I plot it. That's what's in here. So that's nothing but U1, and that's nothing but U2. So I repeat, what's the procedure to apply PCA to images? You take images, you vectorize them, you apply PCA, and then you unvectorize them and put them back to images again. So what does it look like? Well, it looks a little bit perhaps that there is more light in here than there is in there. Do you see that? What does this other one look like? Well, maybe it's from a different angle. But again, you can see that it's darker there in the corners. It's darker on this side. It's darker there. So probably maybe the light is going either from this direction or from the top. It's not entirely clear. But roughly speaking, it simply captures 2 key distinct lighting directions, because that's where the variability of the data is. Okay? So far so good? Now it's the interesting thing though. If I have the average face of someone, and I have, this is the main mode of variation. This is the second main mode of variation. Let's go back to my picture here, right? It's like randomly sample the mean. Here it is. Now I could say, oh, let me sample any random direction here. And I'm going to generate a new phase that could be here, or could be there, or could be there, depending on how much movement do I do along U1. Okay? So that's exactly what we're going to do next. We're going to take here it is. Picture on the top, variation along the first eigenphase. And I go back to the first eigenphase, and I kind of said that it was more light on the right than on the left. So if I start varying in that direction, what happens? Specifically, this is what's done here. I'm going to take the mean, mu, and I'm going to move along the U1 a certain amount. And that amount is going to be between minus sigma and plus sigma, and at intervals of sigma over 3. So in the middle, you just have the mean phase, right? Now the mean phase plus 1/3 of sigma, 2/3 of this sigma, and 3/3 and plus sigma. So now it's illuminated from the right and no light from the left. I went to the other extreme, is the negative version, so now it's the other. So it so happened that by coincidence, the first principal component really captures variations on the lighting from left to right. And by analogy, well, you can see here, it was a little bit harder to interpret, right? But that's the same principle. So, can principal components have a meaning and be interpretable? Yes, they can. But it really depends on the data, because if I now give you another data phase of phases where I vary a lot the light in this direction and just a little bit in this direction, what's going to be the first principal component? It's going to be the vertical lighting. Okay, so it depends on how the data was acquired, and it depends on which dimension in the data has the most variance, because that's what PCA does. So don't think that it has to be super interpretable. Okay. Okay, so that's it for phases. Let me give you another example. So suppose that you take a bunch of MRI scans of the brain. Okay. Suppose that you have someone who is very patient and knowledgeable about the anatomy that goes through those MRI scans and segments them so that you get the hippocampus out. So now, eventually, you get a shape that corresponds to the hippocampus. And now you go ahead and do that for patient number 1, patient number 2, patient number 3, and so on and so forth. Okay. So effectively, now, my data, instead of being images of faces, is 3D shapes of the hippocampi of a number of patients. Okay. So now, again, if these things are not very well registered and they're all over the place, which is the same thing as having pictures of me with my head all over the place, I already told you that PCA would probably not be a good idea, and that because it's not linear. But I told you that faces that are perfectly well aligned changes illumination, that's probably going to work. So by analogy, suppose that you had a very good registration algorithm, and maybe you have no clue what that is, but you can probably imagine that it needs to have them aligned, so that all of the hippocampi are well aligned with each other. And therefore, the only variations are variations in shape. That this might be a little bit thicker there, and the other one might be a little bit thinner there, and things like that. So now, like changes of illumination, there are these little tiny changes in shape. Aging is one such case, where typically they shrink. But actually, they don't shrink uniformly everywhere. There are particular regions that shrink. But that's what I'm trying to say. Or maybe some neurological diseases, you have shrinking in some particular regions of the hippocampus. So there are techniques in medical imaging that are like PCA pretty much, or extensions, that you can just take the average of the hippocampi of all patients to produce an average hippocampus. And that's what's typically become now a template. Now, again with the same idea of taking these 3D shapes and vectorizing them in the same way that I vectorize the faces, you can vectorize them, apply PCA, and then get the main modes of variation. And now, and I wish I had a video because a video is much more compelling, but you can take an average hippocampus and say, what is the main mode of variation? How much does the shape change? And in my face example, it was just changes of light. But here you could start appreciating, like, if all of the hippocampi were from healthy patients, and all what was happening is that the age was the difference. It was a longitudinal study. Then you will see that maybe the main mode of variation is shrinking of these particular regions of the hippocampus. And maybe that's the first principal component. But maybe now, the second or the third, or eventually one of them might be capturing variability of shape that is associated with the disease you're studying. But again, do they need to be interpretable? Well, if the person who actually segmented the images made a lot of errors and lots of mistakes maybe there is a lot more variance due to annotation errors than there is due to biological variability. Or maybe the scanner changed. So that's why you have to never try to read into much the interpretation of what the variable means. But statistically, they have a clear interpretation. They are going to be the directions that are most informative from a variance perspective. That's what they are. All right? Thank you. See you
Thursday.
Thursday.
Yeah.